All right, ladies and gentlemen, we are leaving derivatives behind finally and starting to study integrals. So we'll actually discover in a few lessons that integrals and derivatives are related in this very interesting way. But for now, we're just going to focus on building up a little bit of intuition around what an integral is and why we might want to use one. So I'm posing this problem about a bike workout and how far we travel during the workout. Take a second to read it now. Pause the video if you haven't already. So we are given this information about my speed, and we're looking for the total distance traveled here is what we're trying to find. So this is a very easy problem, except for maybe the units. By the way, this is 3 6-minute intervals, as we can see from the graph. So all I have to do is do distance times speed, right? And that gives me time. And we'll just write everything in hours, right? Just to make our lives a little bit easier. So we'll start with the 3 15-minute high-intensity intervals at 24 miles per hour. And we'll do 3 intervals times 0.25 hours. That's 15 minutes is a quarter of an hour. Times 24 miles per hour. And that ends up being 18 miles. And then we will do the rest intervals. So we have 3 6-minute rest intervals at 17 miles per hour. So we'll do 3 times 0.1 hours. That's 6 minutes is a tenth of an hour, right? Times 17 miles per hour, which is 5.1 miles. And that makes sense because they're shorter and we're going slower. That would be smaller than 18. So my total is 23.1 miles total. So that wasn't very profound, right? That's math you hopefully could have done in middle school. But what's really interesting and what we're really interested in is the connection to this graph here. This, by the way, is a graph that I actually pulled off the app I use to work out. So the question is, how do our calculations relate to the graph? Well, let's start by labeling our graph a little bit since it doesn't really have much data on it, so we can turn it into a little XY axis here, and we know these big humps are going to be 24 miles per hour, and then the smaller ones are going to be 17 miles per hour. This is speed, right? Velocity, we'll call it, and then this is time. And to answer this question, we really want to zoom in on just one particular interval and look at what this graph looks like. So let's look at my last big hump here. So based on what I was given here, well, 24 miles per hour is the height of that little rectangle. It makes sense it's a rectangle, right? Because my speed is constant. And then 0.25 hours is the width, the time, right? Same thing here. If I draw that in again, it's going to be the exact same measurements, right? So notice if I wanted the area of these rectangles, well, I would do 3 rectangles times base times height, right? Now we get the exact same thing. It would be 18 would be my area. And I could do it the same for my smaller rectangles. By the same logic, right, it would be 3 rectangles times a height now of 17 times a width of 0.1 would be 5.1, right? So the answer here to our first problem is the area under the graph in our second problem. And this is the super important insight. So add that to your notes, highlight it, put a star by it, do whatever it is that's going to help you focus in on it, because this is the key insight that's going to be our focus for the remainder of the year. It's this area under the graph represents the accumulation of changes. So the area under the graph of my velocity represents the distance that I traveled. All right, once we got that, all we have to do is learn how to write it down. So we're going to introduce some notation. So again, this is called the integral. And the notation is this kind of stretched out S-boy. So take some practice to draw. This would represent the integral. So that's the symbol, is the integral of f of x is just the function, and then from a to b, these are called the limits of integration. We'll talk about what that means in a second. And then respect to x is just the dx. So read it out loud if you're by yourself, the integral of f of x from a to b with respect to x. Now this looks crazy, but it's not that hard, so it's just some notation that helps you look smart. So what this represents, let's say I have this curve f, a and b are just x values, right? So this just represents the area under the curve from a to b. So let's now try this in action a little bit. So we're going to practice the notation and the idea in this next problem. Oops. So in this next problem, we have a familiar scenario. It's straight line motion. So we have a squirrel running along a wire, and we have a graph of the squirrel's velocity. So if I were encountering this problem in a while, I would right away annotate that we're dealing with velocity here. And we want the distance the squirrel travels between t equals 5 and t equals 10. Let me just mark these areas off, right? And I want to practice the notation here, so I'm going to write out an integral. So if we want the distance the squirrel travels from 5 to 10, well, that would be the integral from 5 to 10, and my leftmost one goes on the bottom, of v is the name of the function, v of t dt, and that would be our distance, right? And notice we have two little areas here. We have this trapezoidal area, and then we have a little triangle down here. Well, we're familiar with both these shapes. We might not remember the formulas. I'm going to give them to you right now, and then we're going to solve our integral. And notice, by the way, this is the same idea, total distance from velocity, as we had in our original example. So here are my area formulas. So we have area of a trapezoid here and area of a triangle here. I'm going to start with the trapezoid in our problem. So our integral is going to be equal to the area of the trapezoid and the area of the triangle, right? So the trapezoid has two bases. So you read this as 1/2 of base 1 plus base 2 times the height. The bases are the parallel sides. So this is b1, b2 up here, and then my height is here. So the first base goes from 5 to 9, right? So that's a length of 4. Plus the second base goes from 5 to 7, so that's a length of 2. And then the height, well, my y value is 7 at that line, right? So that's, excuse me, you're probably thinking the height is actually 20, right, is the y value. And that's correct, the height is 20. So that's the area of my trapezoid. And then the area of my triangle, well, it's going to be 1/2 plus the base is just from 9 to 10, it looks like, right? So the base is 1, and then the height is, let's see, -10? Let's call it just 10, because we can't really have a negative height, right? So here's my integral, but here's the trick, right? We know from our previous work that my squirrel is moving right, when velocity is positive, and then left when velocity is negative, right? So that's going to change my distance traveled. So my triangle area is going to be that negative, right? So we're going to subtract that from the area of the trapezoid, which is positive. So my result here is 75 meters. Just doing the math, and my interpretation is that our squirrel travels 75 meters to the right between 5 and 10 minutes. So that's it. That is our introduction to integrals. It will get harder, but for now, we're using our baby geometry formulas.